Honors Chemistry, this is part 2 of the pretest review video. This is the assignment that will get you ready for the district final, so please do it by Tuesday, June the 8th. It's due on Monday, June the 14th, but get it done before the test. Okay. By the way, this is not just an assignment. It counts as your midterm, so it's 10% of your grade. So be sure to get it done, get it turned in for that purpose by June the 14th. Okay, let's get going. Number 22, what law of thermodynamics is exhibited in a calorimetry experiment by the equation? And the heat going into the surroundings equals the opposite of the heat coming out of the system. That's conservation of energy. That happens to be the first law of thermodynamics, but you don't need to know that it's the first law. It's just conservation of energy is that. Okay. 23. Okay, this is a calorimetry problem that's different than any that I gave you during calorimetry, but it's the same concept. Okay, so a piece of metal with a mass of 400 grams is put in boiling water. After 10 minutes, the metal is immediately placed in 200 grams of water at 40 degrees centigrade. The maximum temperature the water reaches is 50 degrees centigrade. What is the specific heat of the metal? All right, so kind of have to read in between the lines of this question. 400 grams after in boiling water. That means the water's 100 degrees. That means the metal is going to be 100 degrees. So you have an initial temperature, T1, which equals 100 degrees. You have the mass, and we'll write a subscript here, of the metal as opposed to mass of the water, and that's going to equal 400 grams. Okay, then you're going to put it in 200 grams of water, so that's the mass of the water. And the temperature of the water, and this should be for the metal, the T1. So I'll write water out here. For water, the initial temperature is 40 degrees. So what you're going to do is put 400 grams at 100 degrees into 200 grams of water at 40 degrees, and this temperature is going to go up to 50 degrees. Okay, that's what they're saying here. So T2 equals 50 degrees. Okay, so now they want to know the specific heat of the metal. So the formula, anytime you have a specific heat, is Q, that's heat, equals mass times specific heat times delta T, change in temperature. Okay? Okay, so even though this problem looks different than any that we've done, it's really the same thing. You have an amount of water, you have a certain mass of water. You're going to put a hot piece of metal into it. The heat is going to come out of the metal, because it's much hotter than the water is, and it's going to go into the water. So you know the temperature change of the water. It goes from 40 to 50 degrees. You know the mass of the water. It's 200 grams, and you know the specific heat of the water. So from this formula then, you know these three things, you can figure out the heat that goes into the water. That amount of heat is exactly the same amount of heat that had to come out of the metal. So you're going to use this formula a second time for the metal. The Q is going to be the same, it's just opposite sign. The mass of the metal we have right there is 400 grams. The change in temperature, what's that going to be? Well, if it settles at 50 degrees for the water, it's also going to be 50 degrees for the metal. They have to be the same temperature if the temperature stops changing. So that means the metal went from 100 degrees boiling water to 50 degrees. So for the metal, we know the Q, the heat that goes in. That's the same as the heat that came that went into the water. We know the mass of the metal, and we know the temperature change of the metal. So therefore, we can figure out the C, the specific heat of the metal, and that's what the question's asking for. So let's go ahead and do that. So for water, we have Q equals, the mass is 200 grams. C is 4.184. Just to save some time, I'm going to break my rule that I tell you never to break, but I'm going to forget units of measure here. Let's just get through the numbers here. And delta T, it starts at 40 degrees, the water, and it reaches 50. So that's the final temperature minus the initial temperature. And when you do those numbers, that's going to be 200, and I have checked for you, and the units of measure will work out, times 4.184 times 10. 50 minus 40 is 10. Okay, so there we go, and you get 8,368 joules. So that's the heat going into the water. So that's going to be the heat, the negative 8368 is going to be heat coming out of the metal. So for the metal, come over here, it's going to be negative 8368 that came out of the metal. That's going to equal mass. So the mass of the metal is 400 grams. Times C, specific heat. Times delta T. That's going to be 100. That's the temperature of boiling water, so that had to be the temperature of the metal. 100, and it's settled at 50 degrees also, because the metal and the water have to end up at the same temperature. Otherwise, the temperature is going to continue to change. Okay, so it's 100 minus 50. It should actually be 50 minus 100. Don't worry too much about signs here. It's the same thing. It's just 50. It's just the sign changes. Okay. All right. So I assume you know how to do math. To solve for C, you divide by 400, and 50 minus this, we'll go ahead and write it, is going to be negative 50 times C times 400 equals negative 8368. So you're going to divide both sides by 400 and divide both sides by negative 50. So these cancel. So you end up with C equals this. So it's the specific heat is going to be 8368 divided by 400 divided by negative 50. So you're going to end up with a positive number. Specific heat should be positive. So C is going to equal 40.42 if you round that second digit. If you remember from an example we did on one of the homeworks, the specific heat of iron was 0.44. So that's a pretty typical specific heat for a metal. That might even be iron with a little bit of error, just a little bit off from the actual value. Okay, so that could very well be iron. So that's the answer. That's the specific heat, and it should be in joules over grams centigrade. So let's go ahead and write that, joules over grams centigrade. Okay, even though I ignored unit of measure, it's a multiple choice test. They're going to just show you a number. Okay, so that's how you would work that one. Okay, so let's go over that again. Again, it's calorimetry. You can't measure the heat coming out of your system. In many cases in this class, that's been a chemical reaction. In this case, it's a piece of metal. You can't measure that directly. So what you do is you measure the heat going into the water. So the Q, the heat going into the water, equals the mass of the water, 200 grams, the specific heat of the water, 4.184 grams, and the temperature change. The water started at 40, it went up to 50, that's a change of 10. That gives you a heat going into the water of 8,368 joules. That means that's the same amount of heat. Q system equals negative Q surroundings, or vice versa. Negative Q surroundings equals Q system. The numbers are the same though. So that's the heat coming out of the metal. So now we compute for the metal. That's the heat coming out. We have 400 grams of metal. And the temperature went from boiling, which is 100 degrees, the temperature of boiling water, down to 50 degrees. The same that the water ended up with, the metal has to end up with. If it's not, if the metal and the water are not the same temperature, you're going to continue to have heat transfer. You're not done with the heat transfer, so you're not done with the process. In this case, so they have to be the same. So you go from 100 degrees to 50, that's this right here. Okay, there you go. You have one unknown right there, this specific heat. So you just do the math on that, divide both sides by these two right here, and you get this number right here, and that's the specific heat of the metal. Okay, let's move on here. A sample of NH4Cl, that should be a subscript 4, dissolves in water and the temperature of the water becomes lower. Is the reaction endothermic or exothermic? Okay, so the heat had to come out of the surroundings, out of the water, in order for the temperature of the water to become lower. That means it had to go into the system. So that's going to be an endothermic reaction. Okay, if the temperature of the water got lower, we're assuming that the heat of the water didn't go off into the atmosphere. You always assume that in these types of problems. So it had to go into the chemical reaction. So if it made the water cooler, then the heat had to go from the water into this chemical reaction process, and that's endothermic, heat going into the system, into the chemical reaction. Okay, calculate the heat required to melt 50 grams of ice, H2O, using this formula. Okay, this is called the heat of fusion, and it's the heat that it takes to either melt ice into water, a certain amount of ice into water, or to freeze a certain amount of water back into ice. And the formula is very simple. It's the moles of the substance times the heat of fusion. Okay, so let me do that. And I did not give you the heat of fusion on this, so I'm going to have to do that. Okay, so let's go ahead and do that. So it's called delta H sub FUS. Okay, so the heat of fusion for water is 6.02 kilojoules per mole. Really, we should write it, should always get used to writing this directly over like that, so you can cancel units. Okay, so first thing we need to know is it's 50 grams of water. We got to convert that to moles. Okay, that's a molar mass conversion. So 50 grams of H2O times, and you calculate the number of grams per mole of water. So it's 1 mole and 2 hydrogens at 1.01 times 1 oxygen at 16 gives you 18.02. So 50 divided by 18.02 is going to equal 2.77 moles. Okay, so we have moles of H2O, we have our heat of fusion, so now we figure out what that heat is. So moles cancels moles there, so you just multiply these two numbers. And you get about 16.7. And that's the answer. All right, 26. Sketch an energy diagram for a reaction that runs without a catalyst and with a catalyst. So there's 2 lines, very simple. Just asking you to do this. Let's just assume it's an exothermic reaction. So it's going to start here, in order to get it to go from products, so this is energy on this axis, and this is, you could just call it time. It's just how the reaction running. So it's gonna, there's the energy level of the reactants. That's what you start with. You have to put energy in, get it up over that energy hill, and then it comes down, and if it's exothermic, this line will be lower than this line, okay? So that's going to be without catalyst. With catalyst, this and this stay the same, but the energy hill is lowered. It's not as hard for the reactants to get over that hill, and therefore the reaction runs faster. So this one is with catalyst. Okay, and that's all you need to do for that. Okay, when salt NaCl is dissolved in water, which end of the water molecule does the Cl attach to? Positive or negative, oxygen or hydrogen? So there was a PowerPoint slide on this when we dealt with intermolecular forces, ion dipole. So the chloride is a dipole and the water, the chloride is an ion, Cl minus, and the water is a dipole. So it basically looks like this. Here's the water molecule. That's oxygen. There's hydrogen. There's another hydrogen. And this is the plus side because the electrons are being pulled over to the oxygen. And this is the minus side. Okay, so since chloride is minus, it's going to be attracted to the hydrogen side, to the positive side of the water molecule. So the Cl will be right there. This minus is attracted to these pluses there, okay? So Cl is attracted. So chloride ion is attracted to positive hydrogen side of water. Okay, why does a water molecule have a bent shape while carbon dioxide is straight? All right, this is a concept we didn't get to, but you're going to learn it now. So I'm practically giving you the answer. So if you diagram, we learned how to diagram a water molecule. Okay, we did that towards the end of the class. And what we didn't learn was what shape it would take. But what we did learn is the diagram of water. It has hydrogen bonded to oxygen with single bonds here and here. Now what you also have on that diagram that we had was two lone pair here. Okay, when you diagrammed carbon dioxide, and we did that in class, within the last week or so, you had a double bond. I'm actually going to draw this so it looks like a double bond here. So double bond, double bond. There's no lone pairs here and here. What the lone pairs do is they're negative charges. And remember, these right here, there's electrons also here and here. So what these negative charges do is they push down on that. They push down on those electrons. There's no positive charge up here, so it's pure negative charge up here that's going to push down on these electrons, these bonding pairs. So these two lone pairs push down. So they bend the angle down. So instead of being straight like carbon dioxide, the lone pairs push this bond, these two electrons that are right there in the form of that bar right there, they push them down and they push them down. Okay? So that's the answer. So the lone pairs in the water push the bonding electrons down to form a 104-degree angle. That would be this angle right here, 104.5-degree angle. Whereas the carbon dioxide doesn't have any lone pairs on this central carbon, so it stays at 180 degrees. That's a 180-degree angle right there. Okay, that is the answer to that. So that's almost exactly how the answer on the test is stated. So just learn that answer. You'll know when you're at that problem. Okay, what is the electron configuration of neon? Name two ions that have the same electron configuration. So this is something we did in the very last lesson. So you grab a periodic table. And neon is right here. So it's going to be, its first neon has a first orbital with 2 electrons in it. Its first orbital is filled. So a hydrogen helium, so that's 1s2. It's the s orbital. Anything that's over here is an s orbital. The only exception is helium, which is over here. It's also s orbital. Okay. Then you have 2s2 right here. So it's the second row. It's the s orbital because lithium and beryllium are there, so they contribute 2 electrons. So that's 2s2. And then neon is a noble gas at the end of the first row. So this is the p orbital. Again, the second row, the second orbital is broken into 2 different sub-energy levels. An s level and a p level. The p level is a little bit higher energy. And in the p level, there's 1, 2, 3, 4, 5, 6 when you get to neon. So it's 2p6. So that's the electron configuration of neon. So what else would have that? Well, if you take fluorine, fluorine has a 1s2, 2s2, 2p5. But if you added an electron to it, in other words an ion, which fluorine ionizes to -1, then you would have a 2p6. So the answer to this is neon, fluorine with a negative ion, so fluorine minus, you put 1 minus if you want. How about another one? There's another one. You could pick oxygen. If it added 2 electrons, it would have the electron configuration of neon. So you could put O2 minus, or let's go the other direction, Na. If Na loses an electron, becomes positively charged, which Na wants to do, it gives away an electron easily, it will have the electron configuration of neon. So we can put Na plus. So those 3 all have this electron configuration. Remember, ions want to become like the nearest noble gas. Everybody wants to be like a noble gas, and so they all have the noble gas configuration right there. Again, as I said, we could have put O2 minus. If you look at your periodic table, we could have put N, nitrogen, 3 minus. If it gains 3 electrons, it's going to be like this. So I'm putting more than I need to, but I'm just showing you. We could have put magnesium, 2 plus. It loses 2 electrons. It's going to be like neon. So Mg 2 plus. And I'll go ahead and stop there, okay? So those all have this electron configuration the same as neon. That's what they're trying to do when they ionize, is get the electron configuration of the nearest noble gas. Okay, let's come on down here. I helped a lot of you with this problem, and that's because I knew it was going to be on the test. So which one shows hydrogen bonding? So a hydrogen bonding is bonded to either a nitrogen, oxygen, or fluorine, is attracted. Okay, so the hydrogen bonded to a nitrogen, oxygen, and fluorine is attracted to the lone pair on another nitrogen, oxygen, fluorine molecule. So it has to be a hydrogen being attracted to either an oxygen, nitrogen, or fluorine, and being attracted to another nitrogen, oxygen, fluorine. Here you have a hydrogen attracted to another hydrogen. That's not it. Here you have an oxygen attracted to another oxygen. That's not it. Here you don't have any kind of hydrogen bond. You simply have a covalent bond. That's a normal water molecule, and the bond between the hydrogen and oxygen, it's a covalent bond. So that's not it. It's this one. It's a hydrogen which is attached to an oxygen, and this is a water molecule, covalent bond, but it's attracted to the lone pair. You don't see the lone pair down there, but they're there. That's what the dashed line means. So that's an intermolecular force. So this hydrogen's attached to an oxygen, and it's attracted to another oxygen in a different molecule. So the answer is D. Okay, keep going. All right, use the following reaction to answer 31 through 33. Okay, so it's a balanced chemical reaction. We saw that one earlier. You actually balanced that reaction earlier in this assignment. How many CO2 molecules are formed when 0.5 moles of C2H6 are combusted? All right, so what you want to do is write this down and go ahead and draw your graphic organizer if this is helpful. So up here we're going to have moles Here we're going to have molar mass. Those are the translators. And down here we're going to have grams. We're not going to get involved with liters or anything else here, or molarity in this question, okay? So this is going to be mass, and that's in grams. Okay, and we can do one of those boxes for each of these. Now you need to know how to compute molar mass to do this problem. At least maybe you do. It depends on what they're going to ask you. Now the first question they give you, 31, is not one that we practiced really, but I'll show you how to do it. It's really just one additional step. Okay, so you don't have to draw all the boxes, just have those 3 rows. Moles, molar mass, mass. So what's the molar mass of carbon? It's 12.01. Don't count that number, count this number. 12.01 times 2 is 24.02, and that's going to be 6.06. 6 times 1.01. So 24.2, 6.06 is going to get you to 30.08. So that's that many grams per mole of this. O2 is 2 times 16, that's 32. H2O is 18.02, 2 hydrogens and 1 oxygen. Getting those numbers off the periodic table. 2 times 1.01 times 1 times 16 gives you that. Remember, this is not the number. You don't use this when you compute molar mass is for 1 mole. This you use in doing calculations within this specific equation. Okay, and 6 CO2. CO2 is 44.01. Okay, all right. So, how many CO2 molecules? Okay, well, moles is molecules. It's just a big batch of 6.022 times 10 to the 23rd. So what they're asking for is CO2 moles here. And we'll deal with the molecules at the end. Are formed when 0.5 moles of C2H6 are combusted. So that's 0.5. Right there. So we need to get from here to here, from moles of C2H6 to moles of CO2. So the relationship is 2 moles of C2H6 for 6 moles of CO2. So you can write that here. Okay, so remember, you can make 2 ratios out of this. Let's just go ahead and do that. Or, let me put the or over here so I don't take up all this space. The other way around. Just flip it. These are both true statements. Okay, so those are both true. So what are we starting with? We're starting with 0.5 moles of this. So 0.5. And what I should have written is, what are we trying to get to? We're trying to get to moles of C2H4. Excuse me, of CO2. Moles of CO2. So that's what we're trying to find. So we only need 1 box, okay? It's a 1 conversion problem from here to here, jumping over to there. Okay, so which one of these 2 do you put there? Well, you need moles of C2H4 to cancel, and you need moles of CO2 to appear in the final answer on top. So it's going to be this one over here. Okay, so moles of C2H6 cancel. Your last man standing is moles of CO2, so 0.5 times 0.5 times 6, 0.5 times 6 is half of 6, is 3, and 3 divided by 2 is 1.5, so the answer is 1.5. So that's number of moles, but they're asking molecules. So how many molecules in a mole? So we have a second conversion. I'm going to write it up here. 1 mole of anything equals 6.022 times 10 to the 23rd of anything, but in this case we're talking molecules of CO2. All right? So we need to go from moles to molecules, so we're going to start over here with 1.5 moles of CO2. the number that we got at the end of this equation, times 6.022. Unfortunately, there's no abbreviation for molecules. That's probably the biggest reason why I don't give you these types of problems with molecules. Over 1 mole of CO2. Again, this relationship is for anything, but in this case, we're talking about CO2. Okay? All right, so moles of CO2 cancels there, and you have 1.5 times 6.022. And I'm going to just say that is 9.033 times 10. You don't change the exponent. Oops, that should have been times 10 to the 23rd. Sorry about that. So there it is right there. 10 to the 23rd. So this is times 10 to the 23rd. And that's molecules of CO2. That's your final answer. So there's your final answer. That's what they're asking, CO2 molecules. Okay? All right, let's review that. You had to go from, so here's your graphic organizer. You had to go from moles of C2H6, which they gave you, to moles of CO2. That's a one conversion process, okay? You don't have to go to grams or anything else out there, okay? So you end up with a number for that. Then you have to go from that, using this, that 1 mole equals 6.022 times 10 to the 23rd. That's a mole. You have to you do that conversion down here, and you get finally the number of molecules of CO2. Okay? Let's keep going. What mass, meaning how many grams of C2H6 must be burned to produce 25 grams of H2O? Okay, let's go back up here. Let's clean up our graphic organizer. Okay, and they want to know to produce 25 grams of H2O. So here's H2O, so here's the grams row down here. And they want to know how many grams of C2H6, so that's question mark here. So the reaction is flowing from left to right, but this problem is going to flow from here, up to here, over to here, and down here. Remember, here within this box I'm drawing, you're in chemical world. Okay, that's the only place you can move sideways, because that's the only place we know relationships between the products and reactants here. Okay, so again, we're going to start here, use molar mass of water to get to moles of water. Use moles of water to get to moles of C2H6, and use moles of C2H6 to get down to what we're trying to find. Use moles and the molar mass of C2H6 to get down to the mass of C2H6, which is what they want to know. Mass in grams of C2H6. Okay, so we're going to start. What we're trying to find is grams, and this is going to be a 3 conversion problem. So you stretch this all the way across the page here. Grams of C2H6. Okay, right there. And you're going to start with 25 grams way over here of H2O. Okay, and it's 1, 2, 3 conversion. So I'm going to draw 3 boxes. Okay, first conversion down here is this one, 25 to there using molar mass of water. So it's 18. Okay, so there's your relationship. So which one goes on top, which one goes on bottom? You need grams of H2O to cancel because it's not in your final answer. Okay, so you got to put this one on the bottom. Okay, good. So now we're sitting in this box right here, and we need to move from here over to here. So that's moles to moles. So you're inside the chemical equation. You're dealing just with moles. So the relationship is 2 moles of C2H6 equals 4 moles of H2O. Okay, which one on top, which one on bottom? Here, up here. Okay, you need moles of H2O to cancel out because it's not in the final answer. So there it is right there. So 4 moles of H2O goes on the bottom. Okay, moles of H2O cancels with moles of H2O. Finally, now you're sitting in this box right here, and you need to get out to grams of C2H4. That's what the question wants to know. So use the molar mass of C2H4. It's right there, 30.08. So, okay, again, I kind of shortcutted that. What that should really say there is what I wrote here. 30.08 grams of C2H4 equals 1 mole of C2H4. It's the molar mass. It's the relationship between moles and mass in grams. Okay, so which one of these two goes on the bottom? Which one goes on top? Well, you need moles of C2H4 to cancel out. You need grams of C2H4 to appear in the final answer. So we're going to put the grams of C2H4 on the top. So moles of C2H4 cancels there and there. Last man standing is grams of C2H4. So we have everything set up properly. So it's 25 times 1 times 2 times 30.08 divided by 18.02 divided by 4 divided by 1. Okay, this is a pretty big problem for them to give you on this test, so it's going to take a little time, so you want to be sure you know how to do this. It is going to be exactly this question, except the numbers will be different, though. It'll be something other than 25 grams. Okay, so 25 times 1 times 2 times 30.08 divided by 18.02 divided by 4 divided by 1, and I get 20.7. Okay, so this is 20.7 grams right there. That's your final answer. Okay, and that takes care of that. Now we've got another one. 19.5 grams of H2O was actually produced instead of 25 grams expected. What would be the percent yield? Okay, so we never did one of these, but it's easy. All right, so we expected 25 grams. That's what the formula said. But we only got, in the real world, we don't always get what we think the formula says we should get. We get something less. Because why? We waste some, we spill some of that evaporates away. There could be a lot of reasons. So in the real world, you don't always get what you expect to get. So what they want to know is the percent yield. So what that simply is a percentage of what we actually got, this number, of what we expected to get, this number. So it's a very simple equation. It's 19.02, what we actually got. Let me actually write the formula. It's actual over theoretical. It's sometimes called theoretical. That means that's what in theory you should have gotten. Times 100%. So it's going to be 19.02. That's what we actually, 19.05, sorry, 19.5. 19.5 grams over what we expected was 25. That's what the formula told us. Times 100%. So grams are going to cancel out, so you end up with just percent for your answer. And that's going to be, you just do that on a calculator. Do not ever use a percent sign on a calculator. It will mess you up. It's 19.5 divided by 25 equals times 100. And then you slap the percent sign on at the end. So 78, I get 78 for that. And then I slap the percent sign on, okay? There you go. So that's the answer. So you got 78% of what you thought you were going to get. Your actual yield was 78% of what you thought you were going to get there. Okay? Let's keep going. And I'm going to go ahead and wrap this video because it's getting a little long, so I don't like the videos to go too much over 30 or 40 minutes. This one's a little over 40. So I'll see you on the next video.